Hello. Here we're going to talk about end behavior. If you watched the video about asymptotes, we saw that how an asymptote is simply how a graph will behave at its horizontal and vertical extremities. Now what we're going to do is we're going to delve into asymptotes a bit deeper and take a different kind of explanation or approach to understanding how the ends of a graph behave. But first of all, let's define end behavior. It's basically how a graph will behave when x approaches positive infinity and when x approaches negative infinity. Or, in other words, how the left end of the graph will look and how the right end of the graph will look. Okay. So, for example, say you were to have a graph that look like this. There's a horizontal asymptote, a vertical asymptote right there. And say this is at y equals 2. And actually, we don't really care about the vertical asymptote. But when we look at the end behavior, we want to focus again on the left end and the right end of the graph. So in this case, when x approaches negative infinity, y approaches 2. And when I say x approaching negative infinity, when x is getting very negative, when we're going to the left, we see that y is getting very, very close to 2. When x is approaching positive infinity, y is also approaching 2. So as we're going all the way to the right, we see that the y values are getting closer and closer to 2. And that's what really a horizontal asymptote does. Because if you think about a horizontal asymptote, is also considered an end behavior asymptote. So when someone says, oh, it's a horizontal asymptote or end behavior asymptote, I know they're saying the same thing. The equation for an end behavior asymptote is essentially the same for the equation of the graph. And what I mean by essentially, I want to actually put down quotation marks. What I mean by that is that the graph will take on a shape or curve that's similar to the end behavior asymptote. I know it's a lot of writing here, but let's do an example so you see what I mean by all this. We're going to do actually 3 examples today. Okay. Let's say I were to determine the end behavior for y equals x over x squared plus 1. So what we want to do is we want to figure out what happens to y when x approaches negative infinity, and what happens to y when x approaches positive infinity. Now if you were to make a table and say you were plugging like large values for x and small values like negative 1000, what would happen if you actually do this in the calculator is that you would see that y gets very close to 0 in each instance. So that's why I say kind of approximately equal to 0. Another way you could look at this is that x over x squared plus 1 is like saying x divided by x squared plus 1. I know this is going to be a bit mind-blowing, but if I were to actually do long division here, I want to work it out. If I have to figure out what do I multiply to x squared to get x, of course I have to multiply x squared by 1 over x to get that. So if I work it out, I get x plus 1 over x, subtract these two, that goes away, you get negative 1 over x. So essentially, if you think about it, when x gets really, really big, this guy approaches 0. So now we know what the answer is. Y approaches 0 when x approaches negative infinity. Y also approaches 0 when x approaches positive infinity. Other ways we could write this. You could write this as the limit as x approaches negative infinity of f of x will equal 0. Remember, f of x, same thing as y. Over here, the limit as x approaches positive infinity of f of x will also equal 0. So this is actually truly how we want to express the end behavior. All that means for the first one, LIM is abbreviated for limit. As x approaches negative infinity of f of x is your function, whatever it equals, that's what y is going to be when x is going to the left. So y equals 0 when x is very negative. Y equals 0, essentially, when x is very positive or very large. And actually, for you to graph it, the graph would have a horizontal asymptote at y equals 0. So that, again, is another way of expressing your end behavior asymptote when you look at a horizontal asymptote. Let's look at another example. Number 2. F of x equals x over x plus 1. Okay, if x gets really, really big, that's why it's important to do a table. If x gets really, really big, let's say you get 1,000, it's actually going to be pretty close to 1. If you do negative 1,000, it's also going to be very close to 1. So what that means is that the limit as x approaches negative infinity of your function will equal 1. The limit as x approaches positive infinity of f of x also equals 1. And again, x over x plus 1 is the same thing as saying x divided by x plus 1. If I were to actually do the long division, just another way of expressing my function here, if I actually were to compute it, x times 1 gives me x. Subtract it, I get negative 1. So this right here is the same as that right there. They're the same thing. In fact, if you want to find the LCD and do 1 minus 1 over x plus 1, you would get x over x plus 1. Well, if x gets large, for large x, you would just get 1. Because this fraction right here would just go away, or becomes very close to 0 when x gets very large. So that's another way of looking at it too. If you actually do the division, so you can rewrite the equation, when x gets really big, it's pretty obvious that y is just going to equal 1. And also if you plug in numbers yourself, or if you look at the graph, there are a few ways you can actually see it. That's what happens there. Fine for number 3. You have x squared over x plus 1. Again, if I were to plug in a table, if I were to plug in 1,000, y is a very large number. If I plug in negative 1,000, actually in this case, you get a negative large number. Like maybe negative 1,000 or negative 10,000, I'm not sure. Because the bottom will be negative, but the top will be positive if you plug in something like negative 1,000 for x. So in this case, there is no horizontal asymptote. It's not going to level off anywhere. Unlike we saw for 1 and 2. So you have to do long division. X times x gives me x squared. So negative x. X times negative 1 gives me negative x. So for large x, basically x minus 1 is the end behavior asymptote. So it means that the ends of the graph will take on a shape or curve like y equals x minus 1. So the ends of the graph, the left and right end of the graph, will actually be like a linear function. In fact, if you were to graph it, I'm not sure what happens in the middle, to be honest with you. I think you might have something like this here, but essentially what's going to happen, and I totally could be screwing this one up, but the ends of the graph here, and actually let me redo that, that's actually a very poor job I just did. The ends of the graph, okay, one more time, will take on the behavior of y equals x minus 1. They'll start looking linear on those sides. As for how do I write the end behavior, the limit as x approaches negative infinity of f of x is negative infinity, because it just keeps going down. The limit as x approaches positive infinity of f of x will be positive infinity because that just keeps going up. So, and also if you think about y equals x minus 1, it's pretty obvious when x is going to the left, y is going down forever. When x is going to the right, y is going up forever. So you'd write your end behavior that way. So you'll never get a chance to practice this, and of course we'll have a discussion so we can clear up any misunderstandings about end behavior. One last thing that I'd like to put on this to kind of help you understand end behavior. If you have a general rational function like this, if m is less than n, if m equals n, and of course m is greater than n, for your end behavior asymptote, it would be y equals 0, y equals a over b, which is the ratio of linear coefficients, and of course in this case you'd have a slant asymptote, where you need the long division. And that was just like the three examples we did today. M and n being the degrees of the numerator and denominator respectively. So for number 1, you see that the degree of the numerator is 1, degree of the denominator is 2. For number 2, degrees of the numerator and denominator are both 1. For number 3, obviously the numerator has a higher degree than the denominator. So anyway, that kind of covers end behavior. So hopefully you enjoyed the video. We're all done.